Good morning everyone. Let me introduce myself. I'm engineer Luca Ferrua, the operation manager of Fisioline. Fisioline is a company that has been producing and designing electromedical equipment since 1985 and, in this presentation we are going to approach an aspect related to laser technology in the therapeutic field. Now I'm going to share my screen and we're going to see a presentation to shed some light on what laser technologies are, starting from diode sources to the end YAG crystal. So let's talk about laser technologies. We can say that this technology can be substantially applied using either diode sources or end YAG crystal sources. Laser is an acronym. It is the acronym for light amplification by stimulated emission of radiation. So laser is basically a light, an amplification of light by means of a stimulated emission of radiation. From Wikipedia we can go and see what the definition of laser is and what it is made of. The laser is mainly composed of three parts. An active medium that we see here in this graph is point 1. It can be a gas, a crystal, a liquid, which is what it then emits, what generates light, a pumping system. Point 2, i.e. the one that provides the energy to the active medium, and the third part which is an optical cavity, or optical resonator, where light is trapped. So we will certainly have an optical cavity and a mirror, one of which is semi-reflective, from which our laser beam will then come out towards the exit. In particular, in this presentation we are going to talk about solid active media, in particular those that are semiconductors, therefore laser diodes, and then also those that are neodymium YAG sources, therefore two types of solid active media, semiconductors, laser sources, diodic and neodymium YAG, the crystal of neodymium. The laser has various characteristics, the most important are certainly the ones we see now. Directionality, i.e. the laser emits a reaction in a single specific direction. Radiance or brilliance, i.e. the laser can put with a combination of the source, concentrating large amounts of energy in a single point, so watts per square centimeter. Watts clearly is the unit of measurement of the output, of the power, that we are going to use with our laser sources. Monochromaticity, i.e. the laser always emits a single specific color, we will then see which ones can be visible and not visible. And temporal coherence. Temporal coherence means that the laser beam is always in phase, so it is always constant, it is always consistent over time, regardless of the duration of my emission. We can therefore make a comparison with another light, which we are all sure we are all familiar with. By now at home we all have LED bulbs or spotlights. Even the LED is a light like the laser, so both are two types of lights. Both can emit in various colors, red LED, red laser, green LED, green laser, but the big difference can be seen in this slide. It's temporal coherence, because the LED is completely incoherent, it's a completely incoherent light, whereas the laser you see is a light that's always consistent, always in phase, always constant in time, no matter how much I make my laser source work. And in particular with regard to temporal coherence, the laser emits with this, let's say, sinusoidal shape that we all studied at school, which is in this case the distance between the two peaks of the sine wave. So this is our sine wave, the distance between the two highest points of the sine wave. And what is called the wavelength, which is one of the important characteristics that we must consider when we talk about laser technologies or laser sources. Speaking of wavelengths and talking about monochromaticity, we see in this slide that there are a series of wavelengths that are visible and not visible to the human eye. So let's always remember that the emission of a laser light takes place at a specific wavelength, and in this graph we see we have a range that goes from 400 nanometers, the nanometer is the unit of measurement of the wavelength, to about 700 nanometers, so they are wavelengths that have a specific color. So if I use a laser source that will work with a wavelength of, say, 450 nanometers, I will see an emission of a blue color. If we use a wavelength of about 650 nanometers, we will see an emission with a very bright red. Therefore, laser sources operating in this wavelength range, i.e. from 400 to 700 nanometers, are visible to the human eye. All wavelengths that work before 400 nanometers are in the ultra-direct, so they are not visible, and those that work above 700 nanometers are in the infrared, which are also not visible to the human eye. Speaking of lasers and therefore speaking of light, we can say that each color absorbs light. So we can safely give a very trivial example to understand how laser light also behaves. So the classic parking lot of a supermarket in summer, clearly all cars will absorb the heat of the sun and light. So the one that will certainly absorb more heat is the black one, and therefore it is important. When we talk about laser technology, laser sources always take into account the phototype, i.e. the color of the patient's skin. An important aspect when we talk about laser source technologies is the absorption graph. This graph is found in many publications that talk about lasers, and you can see that it is a graph where on the x-axis we have all the various wavelengths of the possible laser sources, on the y-axis the absorption coefficient in function of the first millimeters of skin, mainly in relation to what? Especially in relation to water, which is this blue line, oxyhemoglobin, which is this red line, deoxyhemoglobin, which is this dark blue line, and melanin, which is this green line. And you see that here we find the ranges that we saw earlier as far as wavelengths are concerned, that is, the wavelengths in the visible, which are about 400 to 700 nanometers, those before 400 are the ultraviolet, those over 700 are the infrared. And in this reference graph we find another group of wavelengths, which is the one that is part of the so-called therapeutic window, which goes from about 600 to 1000 to 1300 nanometers. That is, a whole series of wavelengths that are really considered therapeutic from an applicative point of view precisely because they have a series of important and scientific publications, in many journals, which attest to the therapeutic quality of these wavelengths, therefore of those wavelengths that are in this range. Therefore called the therapeutic window. And so you see that each wavelength then has its own specific absorption coefficient as a function of water, melanin and deoxyhemoglobin. Fisioline is a company that can substantially offer diode sources, i.e. those that have semiconductors, and end YAG sources as an active medium, i.e. those that have a YAG crystal as an active medium. Another important aspect is that all our therapeutic lasers have had FDA approval on the American market since 2004. From a construction point of view, working with a diode source and an end YAG source are two different things, because the photon is the same anyway. Suppose, for example, that we take wavelength 1064, we can use a semiconductor as the active medium, so we'll be talking about a diode source, but if we're using a neodymium-doped YAG crystal as the active medium, we're still talking about the same wavelength, but an end YAG source. So same wavelength, but different sources with different powers and clearly different characteristics. Starting from diode sources, we can find two large categories of diode sources, two large groups. The first group is perhaps the most substantial. It is that of continuous sources. Continuous means sources that have a similar peak power, because if I have a continuous source that can deliver a maximum of 10 watts, I will be able to deliver a maximum of about 10 to 11 watts, if I really can't drive the source in a slightly more important way. And so the principle is to have little average power for a long time, so the continuous source is the one that will generate the heat from a thermal point of view, therefore the one that generates the thermal effect on the tissue. And here we will find, let's see later, what are the important wavelengths of these continuous sources. The second type of source is that of pulsed sources, which work in a diametrically opposite way to continuous sources. In fact, pulsed sources have great peak powers, but very low average powers, so they have the principle of having a lot of power for a very short time. So taking an example with our pen, the continuous source will work in mode, so, a little horizontally on this side, the pulsed source will work in a diametrically opposite way, so much tighter pulses with great peak powers. And so the wavelength will also change, and then the thermal and therapeutic effect on the various tissues will also change. Another very trivial example that we can see and analyze is the difference between these two sources, and imagine that we are on the seashore waiting for a ship that has to dock at the port, and we can put ourselves either with our classic torch, and you can clearly see that the torch will always emit. In the same way, i.e. continuous source, the laser does not change its emission mode, it always works in this way. The pulsed source, on the other hand, can be compared to a lighthouse. The light from the lighthouse is spinning, so the ship will see a small dot that will appear and disappear, and this pulsed source will have this great peak power that will already have an important penetration effect from the point of view of the tissues. So this is also the big difference between the two operating modes, between the two diode sources. From the point of view of continuous sources, our lasers have a red continuous source inside them, which is not the guide light, that clearly must be there by regulation, so the guide light is very few milliwatts. This is really a continuous, therapeutic, 650 nanometer diode source, with a power of about 400 milliwatts, so a very low power, very quiet, because the 650 nanometer works in a very superficial way, precisely because going back to the absorption graph, it has a high absorption of hemoglobin, so it works in a very low way. It is very superficial, therefore a practically zero thermal effect, and it is very important to use it to improve tissue regeneration, wound coagulation, rapid healing, so it will generate a very bright red color, very bright, and we are going to use it clearly in the therapeutic field, but especially with regard to the discourse of tissue regeneration, wound coagulation and rapid healing. The second type of continuous instruments that we can also find in our lasers are, let's say, the classic continuous diodes that can operate with various wavelengths, single, double or triple wavelength, depending on which version one wants to evaluate, and we will be able to find these continuous subjects operating at various medium powers and at various wavelengths, in this case with the wavelengths we have available, and they are 810 nanometers, 980 nanometers and 1064 nanometers. Continuous diodes, in particular, can have these wavelengths and with different, variable average powers, which we will see later, and can work in two operating modes. So the continuous diode can work in continuous mode. I can make my source always work over time. How so? Let's look at this chart. X-axis, time, Y-axis, power. I can then, for example, run my continuous source in continuous mode for 2 seconds, let's say at 10 watts. Then I set my 10 watts, my source will work 2 seconds at 10 watts. The average power will clearly be 10 watts, so peak power and average power are exactly the same in this case, because we will be working in continuous mode, so the source always delivers. So 2 seconds at 10 watts and the average power will clearly be 10 watts. However, continuous sources can be fractional or frequencied, some say even pulsed. There are various commercial terms from an application point of view, but let's say the most correct term is to frequency or to interrupt the emission of the continuous source. So my continuous source can always work with a power of 10 watts, but always considering our power and time graph. Instead of making the interval in my 2 seconds, instead of making the source work both seconds, I can make it work every other second. Clearly in this case the average power will no longer be the 10 watts of before when we work in continuous mode, but it will clearly be half, because if a second works and a second does not work, I am going to halve my power, so in this case we are going to introduce a parameter that is present in all laser technologies, but we also find it in radio frequency, ultrasound, magnetotherapy. It's the duty cycle. The duty cycle is nothing more than a parameter expressed as a percentage and is the ratio between working time, divided by working time, plus switch-off time. Therefore it is a parameter in percentage. If the duty cycle is 100%, this is the case, so the laser always delivers. In this case, if 1 second works and 1 second does not work, the duty cycle will be exactly 50%. So, my average power will not be more than 10 watts, but it will be 5 watts, because I will set my 10 watts to the source, but working with the duty cycle, so with an on time of 1 second and an off time of 1 second, the power will be exactly half. So, as far as continuous sources are concerned, the average power depends on the duty cycle, it has nothing to do with frequency. Continuous sources, therefore, can work with various wavelengths. The 810 nanometers, for example, is a well-known wavelength in the therapeutic field, but also in the surgical field. It is the one that has good tissue penetration, but it is the one most sensitive to the color of the skin. If you remember the graph, melanin has a descending curve, so 810 is the one that has the most, in quotes, sensitivity to melanin, to the color of the hair, so it is particularly sensitive to the color of the acute, but from a therapeutic point of view it has an excellent anti-inflammatory and anti-edema effect. The 980 and the 1064 are more or less similar. The 980 is perhaps a little better known in the surgical field, where now, however, we also find a lot of the 1064. 1064 is the most well-known therapeutic method, because like 980 it has good absorption by water, a lower absorption of melanin, so 1064 is less sensitive to skin color, and both have a very important thermal effect. 1064 has the advantage of being less sensitive to the color of melanin, and both have an excellent anti-inflammatory effect. The third diode that we have on our lasers is a diode that is part of the group of pulsed sources. You can see that these sources are also mechanically completely different. Pulsed sources, as I told you before, work with very small pulses, so a lot of power for a short time. So while with continuous sources we talk about pulse widths of microseconds, when we talk about pulse sources we are talking about pulses of nanoseconds, so 1,000 times smaller. The pulse diode basically works with fixed pulses, each of 70 nanoseconds each, with a fixed stable peak power of 300 watts. I can go and use a whole series of these pulses in the span of a second. In this case, how many pulses can I have? It depends on the frequency. In this case, therefore, frequency identifies the number of these small pulses that I can have in 1 second. So we can talk about pulsed working mode when we would have a working frequency of up to 29,000 Hz. With these pulses, with the pulse diode, we talk about superpulsed working mode when we work from 30,000 Hz to 100,000 Hz, but with a pulse diode. So in this case the frequency yes, which depends on the value of the average power. So the average power depends on the frequency, because the more of these pulses I emit in a second, the more my average power will increase. Clearly the peak power with the pulse diode is very high, 300 watts, but the average power is very low, about 1 watt, so a completely a thermal diode compared to a continuous diode. And so, by working with these different frequencies, we then clearly have a different effect on the fabric and also from an application point of view. The superpulsed working mode was born from 30,000 Hz upwards, because we published back in 2007 on PubMed. This publication made precisely with pulsed diodes, which had an effect on bone regeneration, on osteoblasts. So the human osteoblast cell is responding to this working frequency. Therefore, the frequency of work is very important when we talk about laser therapy as far as the therapeutic effect of the various cells is concerned. There are also specific working frequencies from an application point of view, so low working frequencies have an antalgic effect, higher working frequencies have a more analgesic, anti-inflammatory and biostimulation effect. 30,000 Hz is precisely the frequency that gave rise to the superpulsation, precisely the cell responding to this frequency. Before, it had almost never responded to the operational activity of the pulsed source. So 905 has a very good analgesic effect, and also a good anti-edema effect. So, from a thermal point of view, what is the real effect on the skin? Clearly, as I said before, the continuous diode has the thermal effect, so let's heat the tissue a little bit. The pulse diode, on the other hand, is a completely athermic diode, so clearly the effect on the tissues, as well as the from a thermal point of view, but also from a therapeutic point of view, it is different. Fisioline has the possibility of combining these three types of diode sources, which also have various wavelengths, in a single spot in the CPS system, which stands for continuous, pulsed, superpulsed. So we can have the synchronization, the overlapping of the spots, of the various sources that we have inside the machine, through a whole series of terminals, of optics. So we can work with one source, with two sun sources, with three sources, with 3, 4 or 5 wavelengths. The CPS is the possibility that allows Fisioline to realize these lasers with this system, where we have the great peak power of the pulsed sources, 300 watts for each pulsed diode, and the great power of the continuous sources. Then mix, at the same time, the various types of springs. So the continuous diode is the one that will give me the thermal effect, so microsecond pulses. The pulse diode will give me a very low thermal effect, but it gives me a great peak penetration, a great possibility to continue to biostimulate, to give energy to the deeper layers, because it has very low pulses. Small but very high, and therefore the CPS system combines the combination of nanoseconds and microseconds at the same instant to optimize the emission of the various laser sources that we have inside our device from a therapeutic point of view. So it's important to have the ability to take advantage of important wavelengths, which are therefore within the therapeutic window. So the wavelengths that we saw before, 650, 810, 980, 1064, 905, are within the therapeutic window, so they are really therapeutic wavelengths, and then also the fact that we have important peak powers allow us to give and continue to give energy even in the deepest layers, so also to always biostimulate the deeper layers. So having a high peak power is very important to penetrate and reach the deeper layers. In this photo we see how laser light works, a tissue penetration, which is a phenomenon called scattering. We see the diffusion of the waves, the volumetric involvement, through a hand, and we see it basically with an infrared camera, precisely because the wavelengths 980, 1074, 810, 905 are in the infrared. They are greater than 700 nanometers, and therefore when the source delivers we don't see any type of light, we will only see the light guide and the point around it. And so by working with these large peak powers of the pulse diode and working with these various frequency values, we are going to have a very important mechanical effect. Here is also another example, the same amount of water, but if I use it with different pressures, I will certainly have a different effect from an application point of view. Ditto the issue of using continuous sources more than pulsed sources that also work with important peak powers and with different frequencies. From the point of view of the models that we can have available, we have models that use only pulsed sources, models that use continuous and pulsed sources, portable and wheeled. As for models that only use pulsed sources, we have Lumix 100 and Lumix 250. They are wheeled machines with the arm and therefore have the possibility of working with dependent operators or in automatic mode. We have the possibility to adjust the peak power in 3 levels, Lumix 250 from 600 to 2000 watts peak power, Lumix 100 from 600 to 1200 watts peak. The interesting aspect of these models is that they use the photonic interferential emission system, in the sense that the two technologies can work with 2 working frequencies simultaneously, i.e. there will always be the possibility for all protocols to use a fixed frequency of 6 kHz, therefore the classic frequency that can be used at the same time. Used for an analgesic effect, then maybe we will use another frequency up to 100,000 Hz, to have another effect, perhaps a biostimulation effect, an analgesic effect. So we could mix the emissions at different pulsed sources with different frequencies. So we can mix, let's say, the 2 working frequencies. We also have the possibility of exploiting our 400 mW therapeutic red diode for tissue healing, wounds, anti-edema effect, and the average power of these 2 technologies is about 5 W for the Lumix 250 and about 3 W for the Lumix 100. On the other hand, using the CPS system, so let's mix the continuous diodes, the pulse diodes, those various wavelengths and the various powers. Let's talk about the CPS system, which stands for continuous, pulsed and superpulsed. It is a portable laser that has a specific zoom that can be used on 3 levels. So we are going to modify the diameter of the beam to also change the thermal effect that we give on the skin. So we have our 3 diode sources, so we have a 400 mW continuous red diode, which is purely very important for tissue healing and regeneration, the continuous diode that can have powers from 5 to 30 W, with an analgesic, anti-edema, decontracting, draining effect, with the There are 3 wavelengths that we can choose from: 810, 980 or 1064, and the third diode is the pulse diode. We had a 905 nanometer pulse diode, which is the wavelength of the pulse diode, which will definitely have a great analgesic effect, and again a cellular biostimulation effect. From the point of view of the various versions that we can have in the CPS, you see there are a whole series of versions that change depending on the average power and the number of wavelengths, so they will always have our 3 sources. So all the CPSs have a pulse diode, which has a peak power of 3 W and an average power of about 1 W, a 400 mW therapeutic red diode, and then we can have the ability to use 1, 2 or 3 wavelengths continuously with various medium powers. So suppose we evaluate, that we evaluate a CPS 6W, you see that we have an average power of 6W, which will be the sum of 1 W of the pulse diode plus 3 W of a diode working at 810 nanometers, plus 2 W of a diode working at 1064 nanometers, then of course red. So 2 plus 3 plus 1 equals 6. So working with a technology that has 4 wavelengths, we could use 1, 2, 3 or all 4 wavelengths together, with powers ranging from 5 to 31 watts. In this case we have, for example, the 29 watt, which is a laser that works up to 5 wavelengths. So we can have all 5 wavelengths available within our device. These lasers also have quite interesting operating modes. They have a fast working mode, so in case of need we can reduce the treatment time of all the various phases. Of course, all lasers have preset protocols. Clearly, if we reduce the time of treatment, the therapeutic efficacy changes substantially, because we reduce energy. Energy is power for time, so when we talk about laser therapy. So if we reduce the time, clearly the energy will be reduced, so maybe we should do a few more sessions. Then we also have the cold mode, to reduce the thermal effect a bit. Clearly we can already reduce it, as I told you before, by going to work with the consumption in position 3, therefore with a larger diameter to decrease the thermal effect. But if we want, we can also either decrease the power from the application point of view on the program or choose the cold working mode. Cold, which lowers, let's say, the duty cycle and therefore gives a decrease in the thermal effect depending on the pre-selected protocol. CPS can also be in round-up mode. We have two models, the Lumix Plus and the Lumix Ultra, high power, HP. Also in this case we have the possibility to work with the standard automatic protocols, therefore with the ARM, and with the manual protocols. In the CPS, on the other hand, the machine is born with the possibility of working in manual mode, but it also has the option of using, if one wants, also the ARM with automatic protocols. On the other hand, the Lumix Ultra and Lumix Plus have the tone arm as standard. In this case, as for the CPS, also here we have the three types of diode sources with the various wavelengths. It will change substantially the average power and the peak power that I can offer with my technologies. In this case, Lumix Ultra HP will have a peak power of up to 2000 W, because we are going to mount 6 pulsed sources of about 300 W, or more, each. So we have a peak power of about 2000 W and the average power varies from 19 to 35 watts. In this case we can mix depending on the continuous source. We choose various wavelengths and various average powers. In this case we could use lasers that work with 3, 4, 5 wavelengths with a fixed peak power of 2000 watts. In Lumix Plus, on the other hand, we mount 4 pulsed sources, so we will have a peak power of 1200 watts, an average pulse diode power of about 2 watts, and even here we could then mix the various solutions of continuous diodes, thus having the possibility of choosing from 10 watts of average power up to at 30 watts of average power, with 3, 4 or 5 wavelengths depending on the version we are going to choose. Also for Lumix Plus and Lumix Ultra we have the fast mode, so we can reduce treatment times, and we also have the possibility to select a protocol that is perhaps considered manual by default, therefore operator dependent, and make it automatic by going directly to lower the power. So clearly when we talk about mode automatic, we work with very low average powers, below the watt, because clearly the machine works in static mode, so I don't have to give too much thermal effect. By selecting this working mode, the default machine can make a protocol born operator dependent, automatic. So we can use all the functions of the manual protocol, so with all our preset parameters, but in automatic mode. These are the technologies that the company can currently offer with regard to diode sources. The other type of source that we can use, changing the active medium, no longer semiconductors but crystals, is end-YAG. The end-YAG laser is a technology that uses a neodymium-doped nitro-aluminium crystal as an active medium. And it is a crystal that has been known for years, because it was made for the first time in 1964. And this type of laser source uses only a specific wavelength, which is 1064 nanometers. End-YAG lasers are pumped, traditional lasers, with strobe lamps and can work in both continuous and pulse mode. So with the classic strobe lamp, let's see this little video. So let's see how an end-YAG source works. It generates a very important thermal effect. So in some models it is even necessary to cool the tissue because the laser works just like Steinal lasers, so in 3 seconds. Let's start the video. We should then see our end-YAG crystal, the 2 lamps and the reflective optical cavity, the 2 mirrors of which one is semi-reflective. The lamps begin to flash, then to generate our energy as an active medium, the crystal will begin, through the resonant optical cavity, to accumulate. The energy, then it will start to generate our laser light, then the crystal light will start to come out and it will start reflecting off the various mirrors. Through the various mirrors the light will go back and forth when it reaches the important power that we will need, and clearly the very important power, here we are talking about very high powers, will come out through the semi-reflective mirror towards the exit. So this is how the traditional end-YAG works, which has the strobe lamp as its pumping system. Our end-YAG, in this case Lumix Q, uses a completely different pumping system because we have the possibility of working with an end-YAG source that instead of the strobe lamp uses diode sources, so it uses diodes, and therefore we have a completely limited thermal effect, because these batteries will no longer work with a pulse of microseconds at the output, but a nanosecond pulse. Of diodes, in this case Lumix Q works with pulses from 7 nanoseconds to 35 nanoseconds. So it absolutely does not need to cool the skin, and we can work with these very small pulses on all phototypes, even the darkest, without having major problems of thermal effect from the point of view of using technology. And so we have the possibility of having a switched end YAG precisely because it has these very small pulses and with very, very important technical characteristics because we have a neodymium YAG source that works with average powers up to 20 watts, with pulses from 7 to 35 nanoseconds, with the possibility of usable working frequencies from 1 to 100,000 Hz, therefore like the diode sources we have seen before, but above all that it can have very, very high peak powers, therefore up to 130,000 watts of peak power. So we can go and reach, to give a great deal of energy from the point of view of depth and from the therapeutic point of view, that the analgesic effect is almost immediate. And the big difference between diode sources and end YAG sources is also the durability from the point of view of the sources. A continuous diode, a continuous source, can be used for at least 1,000 hours of work. An end YAG source in our case can work up to 8,000 or more hours of work, and that's really a lot. Already 1,000 is a lot, 8,000 is even more. In this last slide, however, we see what is a bit of a summary of what we said earlier. So continuous sources work in microseconds, generally pulses of 5 microseconds, then fairly wide pulses, so those that give the thermal effect. Pulsed sources work with even smaller pulses, i.e. from 70 nanoseconds but with large peak powers, i.e. up to 2000 W. And finally the neodymium YAG Q switched source, which is the one of the Lumix Q. Here we have even smaller pulses, smaller up to 7 nanoseconds but with a peak power of 130,000 watts, so even more important. So this will allow us to still give a very large amount of energy to the depth layers. Well, this is more or less broadly the therapeutic reality of Fisioline therapeutic lasers, which we can offer on our product portfolio and remain at your disposal. Thank you for your attention and goodbye.